Today I am going to discuss about hydraulic design of a gravity dam. So for that purpose I have selected an example from a book by S.K. Garg, Santosh Kumar Garg. Examine the stability of examine the stability of this section at the base. The earthquake forces may be as equivalent to 0.1 g for horizontal forces. Okay, remember this, 0.1 for horizontal forces, 0.05 g for vertical forces. The uplift may be taken as equal to the hydrostatic pressure at the either ends and is considered to act over 60% of the area of the section. A tail water depth of 6 meter is assumed to be present when the reservoir is full and there is no tail water. When the reservoir is empty, also indicate the values of various kinds of stresses that are developed at heel and toe. Assume the unit weight of concrete as 24 kN per meter cube and unit weight of water as 10 kN per meter cube. Okay, so in order to calculate all the required data, that is stresses, so first we have to calculate all the forces acting on a gravity dam. Okay, so there are major forces: dead load, water pressure, earthquake pressure, uplift force. These are all the major forces, so we will be focusing on all these forces. So in order to calculate the dead load, we have to divide this section into number of regular shapes. Okay, so say divide this into a rectangle. Okay, this will be triangle, so this is 1, this is 2, and this is say 3. Okay, so how to calculate the weight of this? The weight of this area, this triangular area, can be calculated by multiplying the unit weight of concrete by the area of this triangle. Similarly, for this part, we can multiply the unit weight of concrete by the area of this rectangle, and similarly for this part 3. Okay, so here it is 6 meter and the height is 60 meter. Okay, here it is width is 7 meter and height is 90 meter. Okay, height is 90 and base is 56 here. Okay, this triangle number 3, the base is 56 and height is not given, so we can calculate the height. How to calculate the height? Height can be calculated by the similar triangle. Okay, we can see that this slope is joined with the top of this. It means that the slope of this downstream face is uniform. Okay, this downstream face is uniform. So in order to calculate, we can calculate it by 90 divided by 90 is the total height, divided by base is 63, multiplied by base of this triangle 56. Okay, so we have calculated the height of this triangle number 3. Okay, so how to calculate the weight? Now in order to calculate weight W1, remember we have to multiply the unit weight with the area. So area will be equal to half into width into 60 into 24. 24 is the unit weight. Okay, how to calculate W2? W2 will be equal to 7 multiplied by height, that is 90, multiplied by 24. Okay, and W3. Please pardon me about the writing because I am not using pen here, so that's why writing will be very bad. Okay, so pardon me for that. In order to calculate W3, so half into 56 into 80 into 24. Okay, so this is how we can calculate the dead load. Okay, self weight of this dam. Now remember, in reservoir empty condition, the forces which will be acting on this dam will be only dead load and earthquake load only. Okay, there will be no water pressure, there will be no uplift pressure because there is no water. And in order to calculate the stresses, we have to consider the worst case. So worst case for earthquake forces will be, now before that, remember, in case of earthquake force, there will be only earthquake inertia forces, there will be no hydrodynamic forces. Okay, there will be no hydrodynamic forces. Why? There will be no hydrodynamic forces. Why? Because there is no water. Since there is no water, there will be no hydrodynamic forces, there will be only inertia forces. Now inertia, now what will be the worst case for inertia forces in case of reservoir empty? When the earthquake acceleration is in this direction, is from upstream to downstream. When the earthquake acceleration is from upstream to downstream, this is downstream, then the inertia forces will be from downstream to upstream. So this will be the worst case. And how to calculate earthquake forces? Remember, the coefficient for horizontal earthquake is given as 0.1. Okay, so we have to consider 0.1. Okay, so earthquake inertia forces for this region, this W1 will be 0.1 multiplied by W1. Okay, multiplied by W1. For this part, the earthquake inertia force will be 0.1 multiplied by W2 and will be acting along this direction from downstream to upstream. And for this part W3, the earthquake inertia force will be 0.1 W3. Okay, now next is to calculate the lever arm. The lever arm for this weight W1 will be this. Yes, remember that in order to calculate the lever arm, we have to calculate it from the toe. This is toe of a dam. Okay, this is toe of a dam and this is heel of a dam. Okay, this is heel of a dam. So we have to calculate from the toe, the lever arm from the toe, because we will be calculating all the moments about toe. Okay, so we have to calculate the lever arm from the toe. So lever arm of this weight W1 from the toe will be 56 plus 7 plus 1. The centroid of this W1, this triangle will be 1/3 of 6. So this will be 56 plus 7 plus 1/3 of 6. Okay, 1/3 of 6. So this will give you 63 plus 2, 65. Okay, so lever arm for this will be this one. Okay, Similarly, lever arm for W2. Now the distance of this centroid from the toe, the distance of this centroid from the toe, so that will be equal to, here, that will be equal to 56, okay, plus 7 by 2, okay, 7 by 2. So this will give you 56, 59.5, है ना, 59.5. And lever arm of this one, so the distance of the centroid from the toe will be so this will be 2/3 of 56, okay, 2/3 of 56. So this is how we calculate the dead load and the earthquake inertia force in case of reservoir empty condition, okay. Here, so I have summarized all the calculations here in this table. So downward weight of the dam W1 will be equal to 4320. All these magnitude is in kilonewton, okay. For W2 it is 15,110, and for W3 it is 53,700 kilonewton, okay. I have considered the positive sign for downward forces. For downward forces the sign is positive, and for upward forces the sign is negative, because the downward force is the stabilizing force. So I have considered this as positive, and the upward force is destabilizing force, that's why I have considered this as negative. Similarly, the anti-clockwise moment will be considered as positive because it is the stabilizing moment, and all the clockwise moments are considered as negative because these are the destabilizing moments, okay. So keep this in your mind, okay. So that's why the downward weight of the dam is positive 4320, and likewise. So by taking sum of all the weights will give you the total weight, total vertical weight of the dam, of the gravity dam. So this will be equal to 73,130, okay. Now multiplying each weight W1 with its lever arm will give you the moment. So since this will produce a anti-clockwise moment, so this is positive, okay. Similarly for W2 and similarly for W3, and sum of all the moment will give you the summation M1, okay, and summation V1 is the vertical downward weight. Similarly, horizontal earthquake forces. So horizontal force is 0.1 W1, so 0.1 multiplied by 4320 is this. Similarly for W2 it is 0.1 multiplied by 15,011, so this will give you 1511, okay, 15110 here, okay. And for W3 it is 0.1 multiplied by 53700, so 0 here, okay. And multiplying each with its lever arm will give you the yes, how can you calculate this one? So okay, I have to discuss it, okay. Let us discuss this one, okay. Now here I want to tell you how to calculate the lever arm for horizontal forces. Now remember, we have to calculate the lever arm from the toe, okay. So the distance of this force, the vertical distance of this force from the toe is this, okay, which is 1/3 of this height. So it will be equal to, the lever arm of this will be equal to 1/3 of 80, isn't it? Similarly for this one, for W2, the lever arm will be equal to this vertical distance will be equal to half of this height, total height, half of this height 90, which will be 45. And similarly for this one, for this one it is 1/3 above base, which is equal to 1/3 of 60, okay, which is 20. For W1 it is 20, for W2 it is 45, and for W3 it is 80/3. Okay, so remember this. Now here you can see for W1 it is 20, for W2 it is 45, and for W3 it is 80/3, that is 26.67. Multiplying each lever arm with the force will give you the moment. Okay, and summation of all these weights, all these horizontal forces will give you the summation H, and similarly for summation 2 M2. Now vertical earthquake forces. Okay, how to calculate vertical earthquake forces? Okay, again we will go back to our previous slide. Here now, in order to calculate the vertical earthquake forces, we have to consider the worst case scenario. Okay, worst condition. So worst condition will be when the earthquake acceleration is downward. When the earthquake acceleration is downward, then the earthquake force will be, earthquake inertia force will be upward. Remember this. Okay, earthquake inertia force will be upward. Okay, but here in case of reservoir empty condition, we have to consider it as, downward force. Okay, we have to consider it as downward force. So the earthquake acceleration coefficient for vertical earthquake is 0.05 multiplied by the total vertical downward force, that is 0.05 multiplied by 73130, and will give you 3695. Okay, and similarly multiplying this by 0.05 will give you this. Okay, so this is how we can calculate the vertical force also. Okay, now move on to our next slide. So in this illustration I have considered reservoir empty condition with vertical earthquake forces acting upward. You can also consider the worst case to be when the vertical force is acting downward. Okay, that may be another case. So for illustration purpose I have considered only one condition, that is when the earthquake force is acting upward. Okay, you can do it at your home when the earthquake force is acting downward, and then you can calculate. Okay, so whatever will be the worst case, then you can understand how you can calculate the forces. Okay, so for illustration purpose I have only considered when the earthquake forces are acting upward. Okay, understood? So when the reservoir is empty and vertical earthquake forces are acting upward, then summation of all the vertical forces will be equal to summation V1, which is positive, and summation V2, which is negative. Okay, understood? So it will give you the resultant, this one. Okay, similarly summation of all the moments, so summation M1, which is anti-clockwise moment, summation M2, which is anti-clockwise moment, because we have considered it like this, horizontal force from downstream to upstream, and summation m3. Since we have considered upward, then the summation m3 will be negative because it will be producing clockwise moment. Okay, so this is the resultant moment. In order to calculate the eccentricity, we have to first consider x bar, that is summation m over summation v, which is equal to this. Okay, now remember that before studying this, before watching this lecture, you have to download the notes and the complete study material of this unit. Okay, the link I have given in this description, and you can download it from my website. So first you have to download this from my website, because only then you can understand what is x bar, what is E, and what are all these formula, what are all the forces. So first of all, download the study material with you, keep it with you while watching this lecture. Okay, now how this eccentricity is calculated: first calculate x bar, and then E is equal to b by 2 minus x bar. Okay, this will give you the eccentricity from the center. This is equal to 12.2 meter. So 12.2 is less than b by 6. It means that the resultant will lie near the heel. Okay, what does it mean? That if it is heel, then the resultant will lie near the heel, and when the resultant lies near the heel, then the tension will develop at toe. Okay, remember this. So now we will be calculating the stresses near toe and near heel. Okay, so how to do that? Here, the formula for calculating the stresses is summation v over summation b, where summation v is the summation of all the vertical forces, summation v is the base width, 1 plus is for compression, and minus is for tension, 6e over b. E we have calculated in the previous slide, and by b. So putting all the values, you will get P at heel is 2070. Okay, P at heel, and P at toe is 60.3. Negative sign is indicating that it is tension, so tensile and compressive. Positive sign shows you compressive stress. So if the allowable stress, compressive stress, is 3000 kilonewton per meter square, then you can very well see that it is in the safe zone, and similarly for the tensile stress. So this is how you calculate the stresses in case of reservoir empty condition. Okay, reservoir empty condition. Now consider reservoir full condition. Now what will happen when the reservoir is full? Okay, in reservoir full condition, there will be additional forces in addition to earthquake and dead load. There will be water pressure, and as well as uplift pressure. So now we will discuss about water pressure and uplift pressure one by one. How to calculate water pressure? The water pressure distribution diagram is triangular, that is hydrostatic pressure. So the variation is shown here. Okay, now the pressure at the top, at the still water level, is 0, and it is maximum at the base, because hydrostatic pressure is equal to gamma W into Z. So at top, at still water surface, Z is 0, so pressure is 0, and at the bottom it is gamma W into H, because the height is, say, H, so it will be gamma WH. So gamma W is 10, okay, H is 86 here, okay. It will give you total value 860. So 860 will be the total water pressure at the base. It is not the resultant, okay. This is the total water pressure at the base, okay. And this is the hydrostatic pressure, so it will be varying linearly like this, okay. Now in order to calculate the resultant, we have to calculate the area of this triangle. This will give you the resultant water pressure, that is P is equal to half into gamma WH into H, that is equal to half into gamma WH square. So this is how you can calculate P. And lever arm, in order to calculate the lever arm will be the vertical distance from the toe, which is equal to this height by 1/3 of this height, that is h by 3. So this will be acting at h by 3 from the toe. Remember, all the resultants, the lever arm of all the resultants will be taken from the toe, because we will be calculating all the moments about the toe, okay. So this is the hydrostatic pressure. Now since there is also a tail water, okay, at height 6 meter, the height of this is 6 meter, okay. So this is say P1, and similarly you can calculate P2, okay. Similarly you can calculate P2 for 6. So this is half into gamma W into 6 square, okay. You can calculate P2 also here. Another force is uplift force. How to calculate the uplift force? Now before that I want to discuss about this part. Since the upstream face of our dam, this is the upstream side, upstream face of this dam is not vertical, it is inclined. So due to this, what will happen, this inclined face will form a water column above this trapezoidal water column, okay. So this will be exerting a downward weight on this face, on the heel, on this upstream face. So we have to calculate this, okay. How to calculate this? We can calculate this by dividing it in this smaller rectangle, say it is W4, and this one is a triangle, say W5, and by calculating the lever arm, okay. So W4 is equal to this, which is equal to 6 multiplied by this height, which is equal to 26, okay. So W4 is equal to 6 multiplied by height 26 multiplied by the unit weight. Now what will be the unit weight? Unit weight is unit weight of water, because it is a water column, okay. So this is how you can calculate W4. And W5, this is a triangle, so W5 will be equal to half into base into height into unit weight of water, okay. Now the lever arm, how to calculate the lever arm? Lever arm is the distance from the toe. which is how much? Up to here, that is 63 plus this 6 by 2. Okay, so it is 63 plus 6 by 2, 3. Okay, and the lever arm of this is 63, okay, plus 2/3 of 6. So 63 plus 2/3 of 6 is 4. Okay, so this is how you calculate W4 and W5. And if suppose we consider this also, this is W6, say W6, so this will be equal to half into height 6 into this is 4.2. How to calculate this 4.2? Again, use the similar triangle. This is slope. Okay, and by using this slope you can calculate the likewise we have calculated in the previous wedge for 3. You can calculate this 4.2. okay, there is no need to tell it other time. Okay, 10. So this is how you calculate. And the lever arm is from the toe, so 1/3 of this 4.2. okay, so 1/3 of this 4.2 will give you the lever arm. So this is how you calculate the weight of water column. Now how to calculate the uplift force? Now since you can see here that the water pressure at the base is 860, okay, and in your question it is given that consider the uplift pressure is acting at an effective area of 60%. So in order to calculate 60% means we have to consider the 60% of this water pressure. So at heel the uplift pressure will be 60% of 860. okay, if there is no if there is no value of this percolation coefficient, this is known as percolation coefficient. If there is no value given, then you can consider it to be 100%, that is 1. Since it is given as 0.6, so multiply 0.6 by this by this water pressure at the base, you will get the uplift pressure at heel. okay, similarly here the uplift pressure here is 60, so multiply it by 60%, you will get the pressure at toe here. okay, so this is equal to 36. okay, and the pressure, the variation of the uplift pressure is linear, so it will be like this. okay, and it is upward, so the pressure diagram is like this. okay, it is upward. Now in order to calculate the resultant uplift pressure, we have to divide this into two parts. First is a rectangle part. okay, so this rectangle, the width of rectangle is 36 and the length is 69. So 69 multiplied by 36 will give you the area of this rectangle. okay, this will be the uplift force U1, which is acting at 69 by 2 from the toe. okay, 69 by 2 from the toe. And in order to calculate U2, how to calculate U2? This is equal to half into this. okay, so 516 minus 36 sorry, multiplied by 69 will give you the U2, and lever arm is 2/3 of 69. This is the lever arm, 2/3 of 69. Okay, 2/3 of 69. So I have summarized this calculation here. Okay, all these calculations are summarized here. You can see weight of the dam. Okay, this is equal to what we have calculated in reservoir empty condition, so there is no difference. Weight of water supported on upstream slope, this is new. This we didn't calculate it in case of reservoir empty, so this is new. So I have already discussed how to calculate this value. So and multiply the lever arm with the load, you can calculate the moment and uplift forces. Okay, now another is how to calculate the earthquake forces. Okay, how to calculate the earthquake forces. Now since this is reservoir full condition, in case of reservoir full condition there are two types of earthquake forces. One is inertia forces and another is hydrodynamic forces. Okay, so we have to calculate both the forces. Now similarly, likewise in the case of reservoir empty condition, the earthquake inertia forces can be calculated by multiplying the earthquake acceleration coefficient with the weight. Now in this case, since the worst case will be when the earthquake forces, inertia forces will be from upstream to downstream. Okay, and the earthquake acceleration is from the downstream to upstream. Okay, okay, okay. In order to understand all the types of forces acting on gravity dam, you have to watch my another lecture which is on the forces acting on gravity dam. Okay, you can watch it, and I have provided the link in the description box. Okay, so do watch that lecture also. So if the acceleration is from downstream to upstream, the earthquake inertia force will be from upstream to downstream, and you can calculate this by multiplying the horizontal acceleration coefficient with the weight of the dam. So you can calculate the earthquake inertia forces. These are the horizontal forces. For vertical force, similarly you can calculate the upward vertical force. Okay, like we have calculated in case of reservoir empty condition. So this will be 0.5 multiplied by the weight. Okay, 0.05 multiplied by the weight. Okay, now one thing which we didn't discuss in the reservoir empty condition was the hydrodynamic force. How to calculate hydrodynamic force? In this example, we will be using the Zenger's formula or USBR formula. Okay, to calculate the hydrodynamic force. Again, the complete discussion on the hydrodynamic force, I have uploaded another lecture on the forces active on gravity dam. You can watch that lecture. Okay, I have provided the link here. Since the height of this inclined upstream face is greater than half of the height of the water, okay, h by 2. If the inclined face is greater than h by 2, h by 2 is 86 by 2, which is 43. So this inclined face is greater than 43. So what we have to do, we have to join this here, okay, like this. We have to join this heel with this, with the intersection of still water level with the upstream face. We have to join this and then calculate the angle. This angle will be theta. So how to calculate this theta? This theta will be equal to tan theta. Okay, here this will be equal to tan theta. 86 is height, okay, this height this height 86 divided by 6, okay, perpendicular upon base. So this will give you the angle, okay. And the cm can be calculated by 0.035 theta by 90, so theta is 81, this will give you 0.668. Now hydrodynamic force can be calculated by 0.726 PE into H. Now what is PE? PE is Cm into KH into gamma W into H. Cm is 0.735 theta by 90, this is 0.668. KH is 0.1 here, gamma W is 10 and H is 86. So this will give you the value 57.5. Putting the value of PE here, you can get the hydrodynamic force, which is equal to this, and moment is 0.3 small pe into h square, okay, or 0.412 capital PE into h, both are same, okay, this and this both are same. So this will give you the value, this one. So this is how you can calculate the moment and the hydrodynamic force. Remember, this is negative and this is negative, okay, understood? So this is how you calculate hydrodynamic force, okay, and inertia force we have also discussed, okay. Here upward vertical earthquake forces are the same, since we have considered upward, so it will be negative, okay, and moment will be negative, okay. Horizontal hydrostatic pressure I have already discussed, this is also negative and moment will be this, okay. This is tailwater P2, okay, P2, and this is P1. Horizontal hydrodynamic pressure, like we have discussed in the previous slide, this is this, okay. And horizontal inertia forces I have already discussed, okay. Negative sign because it is in this direction from upstream to downstream, okay. Now calculate all the summations, summation h1, summation h2, summation h3, summation m5, me, m7, and all the forces. Now here we will be calculating the stresses. How to calculate the stresses? Now you need to calculate, in order to calculate the stresses, first we have to determine the eccentricity E. So for calculating eccentricity we need to calculate the x bar, and x bar is summation m. So calculate the sum of all the moments, okay, sum of all the moments. It is the algebraic sum, so plus minus considering all the signs. So this is the algebraic sum of all the moments will be this, okay. Summation v, algebraic sum of all the vertical forces, okay, this is this, will give you x bar, okay. Ratio of summation m over summation v will give you x bar. B by 2 minus x bar will give you eccentricity, okay. Since this is greater than b by 6, it means that the resultant will be near the toe. If the resultant is near the toe, then the tension will be developed at the heel, okay. So you can calculate the stresses by using this formula, okay. Summation v, summation of all the vertical forces, b is the base, eccentricity we have calculated here, so you can calculate plus sign compressive, and so compressive is near the toe, okay. So this is how we can calculate this. PV compressive near the toe, and PV at heel. This is tensile. Okay. So this is another thing which I want to discuss here is factor of safety against overturning and factor of safety against sliding. Suppose we want to calculate the factor of safety against overturning, then what we have to do? We have to calculate the summation of all the positive moments. Okay, positive means anti-clockwise moment, means resisting moments. So factor of safety against overturning means summation of all the resisting moments. Resisting moments means which are resisting the failure of the structure, those which are resisting all those moments which are trying to overturn the structure. Okay, so these are the resisting. So these are positive, anti-clockwise. Okay, anti-clock. Suppose this is a dam section and this is toe. So the moments which are anti-clockwise about the toe are the resisting moments, divided by summation of overturning moments. Okay, overturning moments means those moments which are trying to overturn. So all the clockwise moments are trying to overturn the structure. Clockwise moments about toe. So we have to take the sum of all the positive moment and sum of all the negative moments, and the ratio of this will give you the factor of safety against overturning. Okay, this should be greater than 1.5. Since this is less than 1.5, it means that our structure is unsafe against overturning. Another is factor of safety against sliding. So in order to calculate the factor of safety against sliding, we have to multiply the summation of all the vertical forces. Summation means, whenever I am saying summation, it means algebraic sum. Okay, so summation of all the vertical forces multiplied by coefficient of friction. Suppose coefficient of friction is 0.7, divided by summation of all the horizontal forces. Okay, so summation of all the horizontal forces will give you the factor of safety against sliding. That's all for now. This is the hydraulic design of gravity dam with the help of an illustrative example. I tried to simplify this example by taking only the major forces. Okay, I have not considered any minor forces, and also I have considered the very simple formula. I have not considered here the shear friction factor. Okay, I have only considered basic formula of factor of safety, basic formula of stresses, of calculating the stresses. I have not considered the principal stresses here. So this is just to give you an idea to how to calculate the forces and how to calculate the stresses and factor of safety. Okay, this is a basic design. Okay, but in addition to that, we have to calculate the shear friction factor, we have to calculate wind forces, we have to calculate wave pressure, we have to calculate other forces also, ice pressure, silt pressure. So I have neglected all these forces. These are the minor forces. One another reason is that calculating all those forces may complicate this example, and you may not understand this well. So I have only considered the major forces. Okay, so keep that in mind. This is not the complete solution to this problem. Okay, dam needs to be analyzed in all those conditions, and there are various methods to check the stability of the dam. Okay, so this is the basic illustration. Okay, do not think that this is the only way to check the stability. This is just a basic, just give you an idea. Okay, so I hope you understood this well. Okay, goodbye.